In this video, we're going to be talking about the basics of an antenna system. So we're going to start off with an omnidirectional antenna and explain the basics, and then go on to more advanced topics, and then hit some of the errors that you might find. So to start, an antenna, which I'm just going to draw as a little circle here, this little red circle, when it radiates energy, it radiates it in two form, and it radiates energy, and there's two parts to this energy. There's the phase and the amplitude. So the phase I'm going to draw in the circle in pink, and the phase radiates uniformly around the antenna, and it does this in rings. So these would all be the peaks, these little pink circles. Alright, now the other part is the amplitude, and unlike the phase, the amplitude is not uniform everywhere. It has peaks and valleys, so you might have this little blue part and then some side lobes, and then a back lobe, which is immediately behind the main lobe, and this one's the main lobe. And then you'll get some side lobes all over the place. So now, what this means is that if you have an antenna, you're going to want to put the receiving antenna and the transmitting antenna, you're going to want them to line up down the main lobe, or what's called the bore site. So, if we come over to here, we have our little antenna, and it's not omnidirectional. We'll make it a parabolic reflector. Let me redraw this. Let's make a parabolic reflector antenna. And so there's our little radiator, and it's going to radiate this way. And then, of course, we're going to get basically a main beam. And this will be a pencil beam in 3 space. So as the energy radiates through space, and on Earth we have air in between, so this air is going to make the signal drop. So if we start off at a reference point of 0 dB, and what is a 0 dB? It's a measure of power, basically. So as we move out, we'll lose power, and so if we're far enough away, we might have 1 minus 135 dB, dBm. Alright, so dBm is another measure of dBs. It's in milliwatts instead of watts. And so a really quick estimation, and this is nowhere near exact, it's just handy. Many RF engineers use it. 0 dB is roughly 30 dBm. It's roughly, this is not a ratio, this is unitless, this is in milliwatts. So this is unitless and milliwatts. Alright, so some errors that you're going to find is if you have two antennas and they're looking both the same way, and this is the transmitter, so we'll put a TX over here, and this is an RX. The main beam this back beam, so here's the main beam, and here's the back beam, and here's the main beam and the back beam. So what you'll notice is the RX does not receive the TX. To remedy this problem, we'd have to make the RX look at the TX, so that way the main beam was focused over there. So the amplitude, so the main beam, or the bore site, they need to be facing each other in your antenna systems. The other consideration is they have to be close enough. Now on a microprocessor, you're not going to be dropping too much power out of these antennas, so they're not going to have that good of transmission range. So you're going to want to keep them within a few feet. If you don't get any signal between the two, first close the gap and bore sight them down, or in other words, point the main beams at each other. And this will give you the best odds of receiving a signal. If you still can't receive a signal and you're pretty close and you're bore sighted in, then you're just going to have to see if your connections are right and if you're really transmitting a signal.